So we were saying here that I want to compare the exact solution, which is a continuous solution. Why we say that it's continuous? Because since we have a function, we can compute the value of velocity at any time we want. In opposition with the discrete solution, the discrete solution will just give us at certain points, which depend on the value of delta t. So we have here, this is a continuous solution, while using the numerical technique, we end up with discrete solution, okay, which will give us values of velocities at certain points. This is why we call it discrete numerical solution. Now, if you compare the values of the numerical results to the exact results, it seems that we have good agreements because the error is relatively small. Okay, we have a little over prediction using the numerical technique, but it's fine. It's nearly acceptable. Okay, so now, for example, from the points, we can, using curve fitting techniques, we can come up with a certain equation. Or here, if you want just to plot it, we can just relate the points and come up with a close solution to the actual one. We have a small difference. If we want to reduce the difference, we can try to use smaller delta t, because you expect that if you have a large delta t, when you want to relate the 2 points, you can relate them by a straight line, you can relate them by a curve. So fitting techniques will be more appropriate whenever you have more points. Okay, so for example, here we can try to use a smaller delta t to see what will happen. And of course, the computational time will increase, but we expect that the accuracy will be better. So for example, here, instead of taking just 6 points, we are using 24 points by using delta t equals to 0.5 seconds. So now, if you, since the points are very close to each other, then you can say that when I relate the points, I will obtain nearly the same curve. So now the agreement is much better. So I was able to come up with a numerical solution that is very close to the exact solution. Okay? So always I should have a compromise between accuracy and computational time. So now no need to try smaller delta t, because if I go, for example, to delta t equals 0.25, I will double the number of points, but still, I already have a good accuracy. So why to have 48 points and more time to compute? Okay, time is very important sometimes. Sometimes it's more important than the accuracy in certain applications, because if you don't choose a proper number of points, you can end up with large amount of computational time, which will lower the efficiency of your solution. So for example, in case you are doing CFD simulations for a space, let's say, here we are talking about just some points from 24 to 48. Maybe for you, no, okay, it's a little bit more time, it's fine. But in real cases, for example, if you have enough space and you want to model the thermal and velocity fields inside, so let's say if you increase a lot the number of grid points inside, so you can come up with, let's say, maybe 1 million element will be fine. If you want to increase the accuracy, let's say, and take 3 million elements, for example, 3 million elements might require 1 week of simulation to give you temperature and variation of flow inside the office. So which is a high amount of time. So you will try to do a grid independence test. When we talk about grid independence test, this means that we will try to select the minimal number of elements that will give us acceptable results. So if I try to go from 1 million to 3 million, and I see that the variation in values is less than 5%, for example, I will say I will stop increasing the number of grids, and I will go for 1 million to reduce the computational time. So keep in mind always the compromise between these two aspects. So in this small problem, we have seen what are the main questions that you will encounter when doing numerical analysis. So sometimes numerical analysis will give us reasonable results. Sometimes no, they can blow up. What do we mean by they blow up? They can give us divergent results. So at the end, maybe in a computer, if you are solving and you are using a non-divergent technique, for example, it will give you this symbol, none. It's non-defined, okay? So in this case, you have diverged from the actual solution. So this is why in this course, we will try to introduce you to the numerical technique. We will tell you which techniques will always converge, which techniques can lead to diverged solution, and how to avoid divergent solutions. We will see how to improve the accuracy of the solution. So for example, in this engineering problem, to improve the accuracy, we reduce the time step. And in this way, we achieve more accurate results. And also, we should keep in mind to save computational time. So we should choose a certain grid size or time step that will not increase a lot the computational time. Okay? So this is in summary, what are the things that we might encounter in engineering problems. For example, also for residuals, let's say for divergence, how you can know that your solution is diverging. Sometimes if you are using a computer just to get a numerical solution, when it gives you a result, if it gives you this symbol, this means that it's non-defined, so it's diverged. In CFD, when you simulate, let's say, a space, we have what is called residuals. Because you know from fluids, you will write, let's say, the Navier-Stokes equations. You have an equation for energy, you have an equation for momentum. What I mean by momentum, so it's for velocity. Okay? All of these equations, Navier-Stokes equations, you have certain differential equation, and at the end, it's equal to 0. So what will happen in CFD simulations, we will convert differential equations to numerical relations by using the schemes we introduced today to go from differential to a certain, if you want, numerical equation. So we replace, for example, dV by dt by delta V over delta T. And then, in this case, we'll have an equation equal to 0, an equation for energy to compute the temperature, equation for momentum in x, y, z to compute velocities in different directions, etc. You will see also that in case you deal with a turbulent fluid, you have additional equations for turbulence. So all of these equations should be solved numerically. And when you solve, you will not get 0, and exactly 0, but you can say, for example, if I reach, let's say, 10 minus 5, you should select a certain criterion. So if I reach 10 minus 5 or 10 minus 6, then khalas, I will consider that my equation is solved. Okay? This number, you will input this number into your software. And once your CFD software try to compute the solution, it will tell you at each step how the residuals are varying. So if you are looking at the residuals and they are decreasing, this means all is fine. And at a certain time, your residuals will go below 10 minus 6. And then at the instant all residuals go below 10 minus 6, your computer will stop automatically and will tell you that your solution is converged. Now, if you are observing your residuals and you see that at a certain time they become to increase, then you will know that your solution is diverged. Of course, sometimes they can go up and then re-go down, so you should wait some time. If the behavior will continue to increase, this means that it's a divergent solution. So based on what you will learn in this course, you will know what to change. You will try to change maybe the grid size. You will try to change the time step in order to avoid having a divergence. So this is a small introduction for the course. Next time, we will start with the first chapter, which will tackle errors, how to compute errors in numerical analysis. Okay. Any question on this for today? Okay, so see you tomorrow. And please try to redo the examples by yourself, and you should try to get the same numerical answers because this course requires practice. Okay. I will post the recordings on a YouTube playlist. Okay, so I will post a link for the YouTube list on Blackboard, and then you can access it from Blackboard and watch all videos of recorded session. Okay.
Thank you, doctor. Have a nice day.
You too. Bye.
Bye, doctor.